Hello, today we will start our exploration of the world of numerical analysis, or also numerical mathematics, or also numerical methods. And I will start with a very simple situation. I have a desk at home, or rather a table, which has a circular shape, and for the sake of simplicity, the diameter might be 1 meter, or another length unit. Okay. People bump into it occasionally, and I'm a little bit worried that there could be some chips around the edges of this table, so I decided to protect the edge. And there is something which is called protective strip. You can glue it around the perimeter, and it really does a good job of protecting your tables and desks and furniture in general. So you go to a do-it-yourself store, and you buy it by length. So what is the length that I really need? Well, when I was a kid, I learned that the perimeter of a circle is given by the diameter times pi. So when I take into account that the diameter is 1, now it pays off, I see that I need pi meters of this protective strip. Now, as a mathematical problem, we've got it solved. We've got it licked. I mean, this is a clear-cut A grade. Wonderful answer, pi meters. But imagine you go to a store and you say, please give me pi meters of this protective strip. Well, I strongly suspect you are not going to get any protective strip because pi is not on the ruler that they use. And that's the key in the practical world, which is not just lay people, but also engineers and people who build things. They need decimal numbers because decimal numbers, that's what they find on their measuring devices. So you need a decimal number for pi, and that's exactly the moment where numerical mathematics steps in. So where do you get such a number for pi? Well, that's actually a very old question. It's several thousand years old. The ancient Chinese were worried about it, Indians, Babylonians, Egyptians, I think, ancient Greeks, of course, and many of them actually came to the same answer. They said that pi is about 22/7. Now I'm going to introduce a notation which I will be using throughout this course, and it's like a wavy equality, or a drunk equality, or a hazy equality, or a fuzzy equality. This means that these two guys are almost equal, but we don't really know what almost means. Okay, this is not a precise mathematical notation, rather it's an engineering notation, or let's say ordinary people notation. We are just saying that these two things look similar. If I take off my glasses, they look the same, more or less. Okay, something like that. So I don't want to make it official. These will be unofficial things which are telling us some ideas. And if we need to make a precise mathematical specification, we will do it using different notation. So ancient whatever, they thought that pi is about 22/7, and I'm going to pinpoint one particular guy, Archimedes, ancient Greek, 2,000 years ago roughly, who not only came up with 22/7, but he also came up with a specific method by which he arrived at this number. It was a method which was based on the analysis of the situation. He actually took circle and he inscribed a regular polygon of suitable shape into it, and he also circumscribed polygons, and he investigated how they behave. And in this way, he actually arrived at 22/7. And this is important for us because that's the heart of numerical mathematics. When we have a problem, we are not just trying to find an answer, but rather we are focused on finding procedures because they are really interesting, because they are versatile. They allow us to answer more questions, perhaps, using the same procedure. We will get to it soon. So numerical analysis, it's definitely numerical methods. That's the main contents. But when you say a numerical method, at the first glance, you would say, okay, it's a procedure for producing answers. But as you can see, we need to add something. So what do we need to add? This wavy shape is the first important point. Pi is not exactly 22/7, but it's slightly different. And Archimedes, when he was thinking about it, he knew about it, because he knew, I mean, you look at a picture, and you can see that the perimeter of this polygon is definitely not the same as the perimeter of the circle. So the method which he used already includes some error which is built into this procedure. And we will call it the error of the method. And therefore, typical numerical method is a procedure for producing approximate answers. Why is it important? Well, because 2000 years ago, 22/7 was a decent estimate of pi. Everybody was happy with it. But as years went by, people improved technology, they improved science, they improved their capabilities of producing more precise machines, things like that. And suddenly, it was obvious that we need a better estimation for pi. So the needs, they change, and even today, people have different needs of precision. A bricklayer has a different need for precision compared to a watchmaker. This is obvious. So when customers come to numerical mathematics and they ask for approximate answer to some question, they also carry with them, they also bring with them their requirement for precision. And that's exactly the moment where the Archimedes approach becomes very fruitful, because Archimedes knew very well that he could actually adjust it and produce approximations of pi of arbitrary precision. So, numerical method is a procedure for producing approximate answers with arbitrary precision. Now, in order to achieve that, what you need to know is something about the error of the method. How does it behave? Where does it come from, of course? So that's an important part of numerical analysis. We not just work about inventing new procedures, because that's, of course, important thing. You need to first invent how to calculate something, how to obtain some answer. But when you develop some procedure for obtaining those answers, the first thing you need to do is to ask, what is the error? Typically, analyzing the error of the method actually takes more work than developing the method in the first place, because this is really the key part. You analyze the error of the method and you get enough information so that you can keep it down when necessary. So the important thing is to have it under control. And only after you can handle the error, this whole thing becomes really practical. Because when a customer comes and asks, okay, what is the square root of 2? If you say it's about 1.4, but I don't really know how precise my estimate is, then this is worthless. You need to be really confident that when you are giving some answer to a numerical question, that you also can say with certainty, and the error which I made is at most this. Is it good enough for you? Yes? Okay, great. And if not, I need to work harder. I need to get a better answer. Okay? So this is very important. But it's not all. You come to the store and you say, okay, I need 22/7 meters of a protective strip. And they say, oh, good joke. Okay. So what you really need is a real number in a form which people can just find on their ruler. So what you need is essentially 22/7 is equal to, let's see, 3.14857142857 and so on. Okay, so this is not going to work very well either, because if you wanted to find precise answer, you would have to spend infinite times working it out. So what you do, of course, you are lazy, and because we are talking here about meters, 3.14 might be enough. So you cut it short somewhere, let's say here, okay, let's be generous. So you cut it short, and you provide this as the answer. That's the number with which you may go to the store now. And this forces us to put here another wave sign and another description. This is the error of calculation. When we are calculating things in a computer, in a calculator, and on paper as well, as you see over here, we typically introduce some errors which are caused by our inability to work with precise objects. Square root of 2 is a precise object, but once you enter it into a computer, it becomes 1.41 blah, 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 something, and it's not precise. That moment, you just created a numerical error. Let me put it here, numerical. This is not an N. Numerical error. And that's another important aspect. And it also has something to do not just with calculations, but also with methods. Because when you are calculating some things which are needed for obtaining the answer, when you are following the blueprint of the numerical method, you are essentially working with imprecise numbers because you are doing it on computer typically. And now the question is, what does it do with the method? How does the method react to those errors? And it turns out that some methods are actually reasonably resistant. So it will throw the answer off a little bit, but not by much. And such a method is called numerically stable. However, some methods are really sensitive to small errors of calculation, and if you don't do something about it, the answer that you get would be totally off. So this is very dangerous, and also it's another thing which has to be studied and kept under control. So the numerical stability, let me put it here, resistance to errors of calculation, that's another important aspect of a numerical method. So in this course, whenever we introduce some numerical method, whenever we invent or develop some way of calculating something, we will ask these two questions, especially the first one, actually. There are some other questions which are typically not as important. One of them is, how much will it cost? To get the answer. Which generally and chiefly refers to time. Time is money, of course. Okay, some calculations can be done quickly, but some calculations takes weeks, months, even years. And this is important to know. Now, typically, the methods which we will meet here, they do not really have to worry about this cost. So we will not really worry about it much, but we will see some exceptions where this third question becomes very, very important. And we will look at it. You will see it in the course later on. So these are essentially the three major questions that we ask about numerical methods. So this, in short, is essentially the outline of what one can expect when you start working with numerical methods, when you start exploring the world of numerical analysis. It's a collection of topics, of questions, for which we are trying to develop procedures for solving them. We are trying to develop numerical methods for solving specific types of questions. And for each method, you expect to see a lot of practical information, which is really crucial. You cannot really do it without them. So that's something that we will see repeatedly in this course. And it's time to start actually doing some serious numerical work. Let's go for it.